Let's look at the integral test to prove a series convergence or divergence. I'm going to provide a link at the end of this if you need a slower explanation, because I'm going to go through this pretty quickly. I'm going to show you an example and give you a chance to try one. But if you need more examples or want to see it worked a little bit slower, I'll link that at the end of this video. All right, integral test says that if we were to, and I better be careful with this. Let me actually put in the bounds here. If we were to take the sequence in here with that pair of bounds and instead be working with the integral with the same bounds, x's instead of n's, these two things, this improper integral with an infinite bound in this series, will both either converge or diverge. They will go hand in hand. If one converges, so will the other. And if one diverges, so will the other. So if I were to just, let's try and get the notation right here, if you remember your improper integrals. If I were to do substitution here, I make u natural log. The derivative of that is 1 over x dx. So you can see I've got the 1 over x right here. So this just becomes the integral of 1 over u du. Of course, the antiderivative is natural log of u. So now going back, if I say, well, okay, that means I've got the limit as b goes to infinity of the natural log of x evaluated at b and 2. Well, plugging in infinity, the natural log of infinity is infinity. So this is infinite. And then you've got the natural log of 2, which, natural log of 2. But it's infinity. This diverges. And therefore, so does this. This is not a test I would use a lot. I would try to avoid it by using one of the other tests. But there are times, especially with natural log, where it is actually a pretty good test to use. All right, pause the video here, and using an improper integral, try and integrate this to see if the series converges or diverges. All right, here's my work. I would once again, go to integral test, say, okay, same bounds. It's going to be e to the 1 over x squared. To have the correct notation, we should do this. I'm going to use substitution. I'm going to make u the exponent, which we typically do when we have e to something. Now the derivative of 1 over x, think about this like it's x to the negative first, is negative 1 over x squared. Well, we almost have that, right? We have like 1 over x squared. If we would add a negative here, we'd have it perfectly, and then we could just offset it with a negative up front. So this would become negative integral of e to the u du. Well, of course, that's just negative e to the u. So kind of going back here, this integral, limit as b goes to infinity, becomes negative e to the 1 over x evaluated at b and 1, like that. Well, if you plug in infinity, you have 1 over infinity, this is 0. E to the 0 is 1, so we've got negative 1, and then we plug, that's a minus, we plug in 1, we get negative e to the first. So we end up with negative 1 plus e, which is not a pretty answer, but it is an answer. Unlike the example from above where we got infinity, this is a number, so this converges. I'm going to put a link here to more examples of integral test. Again, this is probably not one you're going to use very often. You'll probably try and avoid it using other tests. Please like and subscribe for more Try It videos.